Okay, good morning, everybody. My name is Pham, and today I'm presenting some of our work on fiber distribution and alignment in structural UHPC elements that we've done at WJE the last several years. A lot of this work in collaboration with researchers from universities, including Dr. Kyle Riding, Dr. Megan Voss, Dr. Dimitrios, and his students. So for my presentation, I will start with the motivation. I will describe the method that we use to characterize fiber alignment. We discuss some results and then some conclusion. So in terms of motivation, a lot of speakers before me already talked about this. We understand that quantity and orientation of steel fibers can have a significant impact on tensile capacity, UHPC structural elements. The distribution and alignment will depend on many factors. The question that we particularly want to answer is there a simple, a practical method to quantify the effect of fiber alignment? So the method that we use is based on 2D image analysis. So the process will start with sample preparation. So first we establish a reference orientation. For example, it could be the direction of the tensile stress, the direction of the crack in the structures, and then we cut and polish the surface of the concrete in a similar procedures for concrete petrography. And then we took an additional step to treat the surface with copper sulfate solution to make the fiber stand out better from the concrete matrix. We scan the surface at high resolution, and then we develop a MATLAB code that can analyze the image, that can identify fibers based on the colors. We fit an ellipse on each fiber, and then we determine the fiber numbers and the fiber alignment. This is a few images of the bigger image was from the original concrete scan. The image, for the first image, number A to the left, it is the part of the image that we analyze, the original, starting from the original one. And then the image in the middle, B, is after we after the code identify the fibers. And C, the last image here, is the binary image in which we identify all the fibers in a white color from the black background. So in our analysis, we idealize the fibers as cylinders with diameter D, the length of L. Direction X here is normalized, is perpendicular to the cut plane. So on the cut plane, each fiber will have a elliptical shape. So what we can measure is the minor axis A and the minor axis A and the major axis B. And what we want to understand is, based on A and B, can we calculate the angle of the fibers? So we work out the math. So it turns out that A would be equal to the diameter of the fiber, and B is diameter of the fiber divided by cosine theta. Again, theta is the angle between the fibers and the reference orientation, which is the orientation perpendicular to the cut plane. So what are we going to use? So we can determine the angle theta, and what are we going to use theta for? So in here, the two blue line here represent two fibers that oriented at angles theta 1 and theta 2 from the reference axis, which is the vertical axis here. So what we want to understand is the contribution of the fibers to the reference orientation. And we consider that contribution of each fiber proportional to the projection of that fiber to the reference orientation, which turns out to be cosine theta. So we make a cut through the sample. We can measure, we identify, say, 100 fibers. We can calculate the cosine theta for each fiber, and then we take the average of all the fibers. And that basically represents the average contribution of the fibers to the reference orientation, which we call the factor K here. And then we also calculated a factor, what we call fiber alignment factors, which is K times fiber density, which is basically the total contribution of all the fibers on the cut plane relative to the reference orientation. So that is our method. We're going to use this method to look at relationship between fiber alignment versus flexural performance versus direct tensile test, and also versus shear performance. And then we took another step to look at to compare our 2D analysis with 3D analysis, which was performed by other researchers. So to look at the fiber alignment versus flexural performance, what we're seeing here is a 10-foot by 10-foot slab by 4 inches thick. The UHPC was poured at one fixed point from one end of the slab and was essentially allowed to flow freely to the other end to fill the slab. So after the concrete was hardened, we have 6 beams cut out of the slab, 4 by 4 by 12 inches, in 2 groups. So the first group are the 3-beam ABC, which was essentially parallel to the flow of the concrete. And the other group is D, E, and F, beam D, E, and F, which were perpendicular to the flow, essentially. So with some sample, after some sample preparation, we tested these 6 beams in flexural using the 1609, basically 1609 procedures. So the table here showing the result of the flexural test for both first crack strength and peak strength. The 2 lines at the bottom of the table here showing the average result for the 2 groups. Again, the first group A, B, and C were parallel to the flow. D, E, and F were perpendicular to the flow of the concrete. And it was no surprise that we have the first group has higher flexural strength than the second group, right? So our question is, that is the flexural result. Can we find a relationship between fiber alignments based on our 2D image analysis with the flexural performance? So we make a cut through the beam at a cross section near the. So after the beam was tested, we made a cut through the beam at a cross section near the flexural plane. So this is the images of the 6 beams that we tested. We calculated the alignment factor K, axial alignment factor K, and the fiber alignment factor F. And we put them on a plot. And so all the blue dots here represent the first crack flexural strength. The red dot represent the peak flexural strength. And we found some moderate correlation here. It's not perfect, which suggests that there are other factors that affect flexural strength and behavior other than fiber alignment. So in the next group of result, we look at fiber alignment versus direct tensile test performance. So the plot here showing the stress strain curve for a pair of direct tensile test samples. These tests were done by Dimitrios and his students at the University of Houston, and we're grateful that they allow us to use these results for our presentation. So in the plot here, you see that the blue curve represents a sample showing strain hardening behavior, and the red one showing a strain softening behavior. And here's another test for another pair of samples. Again, the blue one is strain hardening, and the red one is strain softening. So after the sample was tested, we also made a cross-section through them. We did image analysis. We calculated on the top plot here is the fiber alignment factor, the factor F that we talk about. Pretty good correlation between the fiber alignment factors versus the strain hardening or softening behavior. The lower plot here showing the fiber density, a pretty good correlation as well. Okay, so the next group of result is between fiber alignment versus shear performance. So what you're seeing here is a UHPC beam, 4 feet 8 inches, pre-stressed concrete that was tested and failed in shear. So one noticeable thing about this beam was when the beam was placed, the point of displacement was moved along the beam to facilitate the flow of the concrete. There was a story behind it, and I don't want to go to I don't want to go into the detail about it, but that was what it was placed. That was how the beam was placed. So, and then the beam was tested with the load at the midspan, and the beam fell in shear. And on the right side here, you can see that a diagonal crack, a huge diagonal cracks, which looked much bigger when you tested it. This is the crack obviously closed after you remove the load. But the beam fell in shear. What you're not seeing in these pictures is another crack on the other side, diagonal crack, but the crack was much tighter. So the beam was predominantly fell in shear on the right side. So after the beam was tested, we took 2 cores out of the beam. The core 7-2 here, next to the crack, next to the failure crack, and the core 7-4 here, location 4 here. It's next to another crack here, but a tighter, much tighter crack. So we took the core, we make the cross section, and the cross section parallel to the direction of the crack. And we calculated the fiber alignment factors and the fiber density for the two samples. And as you can see here, at location 4, both the fiber alignment factors and the fiber density were much higher than at location 2, which is consistent with the shear test with the test result that we got. So the bottom line is, because of the placement method, we believe that most of the fibers, the majority of the fibers, tend to orient in the direction of those orange line there because of the placement method. So what it means is at location number 2, more fibers will tend to parallel to the crack. But at location 4, more fibers will tend to be more perpendicular to the crack, which help with the shear behavior. So pretty good result. And then we took one additional step when we compare our 2D image analysis with 3D analysis done by other researchers. So a little bit of mathematically background. In a 3D space, if all the fibers are randomly oriented, the likelihood of a fiber oriented at a certain angle, theta, will follow a sine theta curve. So what I'm showing here is basically the population of the angle of the fiber from 0 degree to 90 degree. It follows a sine curve. Now, when we did our 2D analysis, we took an additional step, which is the cut plane that we make through the sample. And when we make a cut through the sample, the fibers that tend to parallel to the reference orientation, they have higher likelihood to be cut by the plane. Whereas the fibers that kind of flat here with a larger angle larger deviation from the reference orientation, which is the vertical axis here, they have less chance to be cut by the cut plane, right? So we introduce an effect from by the cut plane. So we work out some mathematical calculation here. So at the bottom line here is in the 2D analysis, the probability of the angle of the fibers change. The population of the angle change from cosine theta, from sine theta to cosine theta. So the plot here basically showing the distribution of the fiber angles from 0 degrees to 90 degrees for a 3D analysis and for a 3D analysis. So we will expect some differences between a 2D and 3D analysis using the same fiber alignment, axial fiber alignment factor K. So we compare these, the K value here between 2D and 3D for 3 hypothetical scenarios that we can calculate the value of K theoretically. So we look at 3 scenarios. The first one is all fibers are aligned in the direction of the reference orientation. Both K equal to 1. We look at a situation where all the fibers are perfectly random. Then we saw a difference between 2D and 3D. And then on the other scenario, where all the fibers perpendicular to the reference direction, the contribution of the fiber is 0, right, in both cases. So in the middle case here, we saw a difference. So in order to compare between the 2D and the 3D analysis, we use a simple quadratic equation to kind of normalize the 2D alignment factor K, and we call it K prime. And then we consequently, we also have a normalized fiber alignment factor. So to compare between 2D and 3D, we got 10 cores taken from different UHPC members. The 3D image analysis was done by Dr. Kite Riding and Megan Voss. And then we compare the results. So the first result you're seeing here is basically represent the fiber content in the concrete based on 2D analysis in the vertical direction, in the y-axis, and on 3D, in the 3D analysis on the x-axis. And they all within about, around 2% of the fiber content, which makes sense. And they're fairly close. And then the next result, we compare the axial alignment factor between 2D and 3D without normalization and with normalization. The normalized one, much better correlation there. All right, so with that understanding, with that knowledge, we went back to reanalyze the flexural beams, the 6 beams that I talked at the beginning, from A to A, B, C, D, E, F, without normalization, and with normalization. However, in this case, the normalization turns out to be doesn't make much difference of the correlation. Again, it suggests that there are other factors that could affect the flexural strength of the beam other than fiber alignment. Okay, a few key takeaways. Again, our work here kind of verify and confirm and provide additional evidence that fiber alignment and distribution are both important for performance UHPC elements. The 2D image analysis that we developed is a practical method for characterization of fiber alignment. The fiber alignment factor that we got correlate with flexural, tensile, and also shear performance. Between 2D and 3D, the factors correlate well, provided that the 2D parameters is appropriately normalized. And there could be a variety of application for this analysis. It can be used to evaluate effect of UHPC placement and also UHPC materials characteristics on fiber alignment. It can be used for research, investigation, troubleshooting. You tell me. So with that, I would like to acknowledge the contribution and the help from the researchers for our work here. I'm happy to take any question.